Yeah, it's a long title for a very preliminary work. And then also, as you said, I work for Nokia Bell Labs. But this work I present is part of my individual research, I would say. It started when I was working at Mellon University. And then I continued. So I'm not reflecting at all any of the company position about this topic or any of that. That's my disclaimer, especially if it's going to be recorded. Okay, but what is true about this field is that I come from a background in all these little things that I put here: vehicles, drones, transportation systems, etc. So the problems I'm facing come from these domains also. And they have to do with deterministic communication. So I will explain a little bit about that. And then I will go into the morphogenesis aspects of it. I think I need a little bit of background for everyone. In our community, when we say deterministic communication or deterministic computation, is what we call real-time systems. We mean that we are assuming, first of all, a Newtonian time framework. Normally we call it the timeline. This is like a fabric of time that is, all the properties. And what our concern is that we want to guarantee that the start and the end of the communication and computation activities happen in specific places over this timeline with great accuracy. So what we mean by determinism is temporal predictability of this. Because this predictability is very important in order to achieve control and other interesting properties. Okay, the most normal type of real-time system is the one in which you said that you have satisfied deadlines. So we are not so concerned about when things happen, but once they happen, they need to be taken care within a deadline. This is the most common definition. Okay. So there are many ways to guarantee these properties, to achieve determinism. In this talk, I focus on one of the most popular paradigms, which is called the time-triggered paradigm, which is not so well known outside the community, but inside the real-time systems, everybody knows about it. It's one of the foundational theories developed by Hermann Koppitz. And it's based on static information structures or patterns. And it sacrifices flexibility for predictability. And the consequence of this is that it is difficult to adapt to changes. Or if you adapt, you do it at very high cost. And I think this is an interesting starting point because what I have reached is a point in which I'm asking myself, did we build this paradigm correctly? Because we are facing some complexity issues as these control systems grow in size and in number of elements interconnected. We are facing issues, and I'm wondering if it's time to extend this with new concepts. And can we get any inspiration from biology, from morphogenesis studies? Because this form of communication is based on patterns, so I think it's just natural to look into pattern formation in biology, how it happens, why it happens, etc., and in which way we can use it. But I will continue a little bit more with the background to explain what are these three structures that we are building. This paradigm is based on three elements. First is the clock, the common timeline. We are having issues now. You see, I can make the parallelism with our conference now, this workshop. We all have different clocks, and we need to synchronize. No, like, okay, what time according to which reference in 20 minutes, 10:30 in Sweden or in Japan, or we need to. And then on top of this common timeline, once we understand that we are using the same timeline, we are defining the slots. So we are saying, okay, this is the slot for the keynote, this is the slot for the coffee break, this is the slot for the next of the talks, etc. So this communication works like that. And the thing is how you assign the messages to these slots, and this is what is called scheduling. In scheduling, we basically assign messages to slots, and we say this is going to happen here. It can be transmission of messages, it could be computation of tasks, but basically you assign statically where things are going to happen, so everybody knows. One example, for instance, when it's a little bigger, here, imagine you have a network with 6 nodes, and each node is connected through a link. I put them individually because the direction matters. So link 1 goes from node 1 to node 3, link 7 goes from node 3 to node 5. So here we can define the slots on the horizontal line. For instance, we can say, okay, we're going to use 8 times slots. Everybody needs to agree on the beginning and the end of the slots, and then everybody has to agree on what is going on. For instance, here we say that in slot 1, over link 1, this node will send frame number 1, and then in slot 2, this link will send this frame, etc. Okay. Once you have it, it works very well. It's very efficient, and you can use schedules with different properties. For instance, this is the first one, minimizes the waiting time in the queues. This second, for instance, tries to spread, is more like load balancing of the messages, etc. So you can apply different strategies to solve these problems. But in general, the scheduling happens in abstracto. It's a symbolic representation of the problem. So we start with this symbolic representation in which you have the network topology, traffic requirements, slot size, and the scheduler performs what we call synthesis, which is normally some kind of constraint programming, satisfiability solver, sometimes genetic algorithms, whatever you want to use. And the result is the schedule, which is a solution that I call in abstracto also, because it's based on this previous definition, symbolic solution. And then the solution is embodied through deployment. Okay, and here I'm not representing it, but it works only because of the faithfulness of the model. We know that the deployment of the symbolic solution works because we know that the architecture implements these structures very reliably. Okay, it implements the time slots, clock synchronization is already solved, etc. Okay. My finding in the last month is that in biology, this is exactly what is called the positional information paradigm. And here I just copied and pasted from this seminal paper by Wolper in 1969, how he explains something that regards the morphogenesis, no? the genesis of organs and tissue, etc. And then he defines, he was an engineer, by the way, he defines a gradient as the factor that triggers and stops the generation of certain cells, etc. So, so you can see the parallelism. The only difference is that for us, the gradient is time itself. So this fabric that we built, which is the real time, is where we are going to have a gradient, which is the clock and the slots, and we are going to assign. Okay? And what is the problem with that? The main limitation is that it doesn't adapt. For instance, if I break this link and the messages that were going through link 7 cannot go, the natural solution would be to say, okay, let's find another path. Let's send from 5 and 9. But what happens with this? This structure was static and cannot be changed dynamically. So how do we handle this? The solution right now is also symbolic. That's why I say adaptability is handled also in abstracto. We have a symbolic representation of the possible faults. We have a symbolic representation of the possible changes in traffic, etc. And we feed all that to the scheduler, increasing the level by 1 or 2 orders of magnitude, the complexity of the problem. Another scheduler is not generating only one solution in abstracto. It generates several symbolic solutions that they can all be combined into one solution, but you can also divide them into different schedules that might represent different operation mode changes, failure modes, etc. Okay, and then we embody. With respect to embodiment or deployment of the solution, one solution is that is fast but non-exhaustive is to compute as many solutions as possible and preload them. So you need to have memory, you have to have them already in body. And then the other is exhaustive, but it's slow, is that compute the solution online and do it only after failure detection. So it's slower, the reaction time is slower. Okay, so in a paper, very recent paper in 2021, we presented something we call self-healing protocol, which is a distributed protocol to repair the schedule that divides this problem, the synthesis problem, into a number of independent partial synthesis problems that are resolved on the node. Obviously, there is no time to go into details, but what we do in this approach is to transfer the responsibility of generating the solutions to the nodes, such that they can do local computations to find the piece of the solution that they need to provide. So in this sense, it's a collective intelligence. The nodes solve the problem locally, and altogether it works. Okay, but still, with this solution, we can only change the schedules. So if there is a link failure, we can distributedly find a solution that uses different links by changing the schedules. The questions we're asking now is, can we have also emerging slot divisions and sizes of these slots? Like why not to go a little deeper into this adaptability and make the slots also self-healing or emerging? Why do we have to start with a static definition of time? And when we look into biology for inspiration, we see that the PI paradigm, the positional information paradigm, is just one of the possible models for morphogenesis. Yesterday, there was a very nice discussion about this. There is also reaction diffusion mechanisms that Turing talked about, and there is the clock and wavefront mechanism. It has been studied also very recently. So what can we do with that? Then what about emerging clock synchronization? Do we really need this fabric of real time? Do we really need to have a global clock? Because in practice, guaranteeing this global clock is also problematic when you have many nodes and changing conditions. And then when you look into biology, and I looked into biosemiotics, they showed that global clock is not required at all for coordination. There is not such a notion of global clock in nature. What you have is intersubjective synchronization. You have interaction between peers that are building this coordination or these symmetries dynamically. So this also connects with the notion of symmetry. Is clock sync? The question here is that, are we imposing clock synchronization in order to achieve symmetry instead of tackling symmetry from the beginning and discussing about symmetry, and then let emerge clock synchronization as one of the possible solutions, as one of the possible patterns to achieve this symmetry? What is there? What is hiding in them? Okay, so this is the main problem I'm thinking about these days. There is a lot to think about this embodiment of morphogenesis with respect to determinism in time. I believe the parallelism between time-theory communication and pattern formation is evident. As far as I know, nothing has been done about it. I don't know of any research. I am inclined to believe that our solution is some form of clock wavefront mechanism, because we are creating a dynamic gradient between the nodes when we detect a failure that triggers certain processes that lead to repair. But of course, I cannot prove that yet. And I think also I learned yesterday about homeostasis. I think that's a step forward to express determinism as that. Also that the emergence of synchronism by intersubjective interaction, I think it's an exciting challenge because it goes against the tradition in real-time systems. For the last 30, 40 years, everything is based on global clocks and global synchronization. So I think that challenging that view is a very, very exciting possibility. And thank you. This is